You have learned that during physical process like phase transformation, it is possible to attain equilibrium. Similarly, when a physical process like dissolution is taking place, it is possible to achieve a state of equilibrium. There are two types of dissolution: gas in liquids and solid in liquids. Sugar in water is a classic example of solid in liquid equilibrium. First, sugar is added to a glass of water and stirred. It dissolves, forming a sugar solution. Then, as more and more sugar is added, it initially dissolves, but eventually reaches a stage where no matter how long you wait or how vigorously you stir, the sugar does not dissolve. The solution thus obtained is said to be saturated at the given temperature. Thus, at a given temperature, a solution that remains in contact with excess solute is said to be a saturated solution. In a saturated solution, a dynamic equilibrium exists between the solute particles in undissolved state and the solute particles in the solution. When the solution is kept in a closed system, the concentration of the solution and the amount of undissolved solute remains constant in the solution. The dynamic nature of this equilibrium can be established using radioactive sugar. Let's see how. Take a beaker containing saturated sugar solution. To this, add a small quantity of radioactive sugar and let the solution remain undisturbed for some time. Then check the solution for radioactivity. It is noticed that both the undissolved sugar as well as the solution has turned radioactive. This is a result of dynamic equilibrium, where the molecules of the radioactive and the non-radioactive sugar from the solid and liquid phases are being exchanged. This proves that there is dynamic equilibrium when a solid is dissolved in a liquid. Now let's look at the equilibrium involving the dissolution of gases in liquids. Have you ever wondered why soda fizzes when opened? The fizz that bubbles up when you open a soda water bottle is carbon dioxide gas. The phenomenon of fizz you see in carbonated beverages is due to the difference in the solubility of carbon dioxide at different pressures. At a given pressure, equilibrium exists between the carbon dioxide molecules in the gaseous state and those in the dissolved state in the liquid. This equilibrium is governed by Henry's law, which states the mass of a gas dissolved in a given amount of a liquid at any temperature is directly proportional to the pressure of the gas present in equilibrium with the liquid. All carbonated drinks are bottled under pressure to increase the solubility of carbon dioxide in the solution. When the bottle is opened, the pressure above the solution decreases. To reach the new equilibrium condition under decreased pressure, some of the dissolved carbon dioxide escapes. This gives rise to the fizz that you see when you open a bottle of carbonated drink. This is also the reason why the taste of carbonated drinks turns flat when the bottle is kept open for some time. Thus, we can summarize the general characteristics of equilibrium in physical processes as: at atmospheric pressure, a solid exists in equilibrium with a liquid only at one temperature, which is called its melting point. For example, at atmospheric pressure, ice exists in equilibrium at 273 Kelvin. At a given temperature, vapor pressure remains constant for liquid-vapor equilibrium. For example, in equilibrium between water and water vapor, the vapor pressure of water remains constant at a given temperature. At a given temperature, solubility remains constant for the dissolution of solids in liquids. For example, at the given temperature, the solubility of sugar remains constant in a given liquid. At a given temperature, the concentration of a gas in a liquid is directly proportional to the pressure of the gas over the liquid. For example, the concentration of carbon dioxide in water at equilibrium is directly proportional to the pressure of the gas over the liquid. At a given temperature, equilibrium can only be achieved in a closed system. For example, no equilibrium is attained when water in a beaker is kept open to the atmosphere. This is because the rate of condensation is much less than the rate of evaporation. At equilibrium, both the opposing tendencies occur at the same rate, and hence, a dynamic yet stable status is established. For example, for water at a given temperature in a closed vessel at equilibrium, the rate of evaporation is equal to the rate of condensation. At a given temperature, the attainment of equilibrium for a physical process is characterized by a constant value of one of its parameters, such as vapor pressure, melting point, solubility or concentration. For example, during equilibrium between liquid and gaseous water molecules, the vapor pressure of water remains constant at a given temperature. At equilibrium, all the measurable properties of the system remain constant. For example, for the solubility of solids in liquids, the solubility remains constant at a given temperature.